Hello and welcome. Today we're going to talk about conjugates, the triangle inequality, and polar coordinates, and moduli. A lot of what we're doing here is fairly basic stuff, and it's largely definitional. Okay, so let's just start off with some perspective on this. What we want to do is we've been talking about complex numbers, z, and we write them x plus I, y, and we think of them as a vector in the plane, right? So we think of them as a vector. All right, so we can write that like that. Stick it up there, and we have an ordered pair x comma y. All right, so like any vector, vectors have usually we think of them as a direction and also a magnitude. All right, so we have to find a way of measuring these ideas of direction and magnitude, and the first definition we have today is that of the complex modulus. And that's simply what we'll use. The symbol for the complex modulus is just what we call the absolute value signs. Now, of course, complex numbers don't have an absolute value because they have this imaginary component to them. But we think of them actually as basically just the distance along this line here. So we think of that as z as being this distance right here. Okay, and of course we get that by taking the square root of the sum of the squared components. Very straightforward. It's just like what you would do anytime you're dealing with finding the length of something in a plane. You just use the Pythagorean theorem essentially. Okay, so that's the complex modulus, and that's pretty straightforward to use. So anytime we see the symbol, this absolute value, what we really mean is the length of the vector in the complex plane. So that's our first definition. The second thing we're going to talk about is that of a complex conjugate. So when I say a conjugate, that word, if you look it up in the dictionary, it just means that it usually means that two objects are paired in some very important way. So a complex conjugate is, so if z is equal to x plus I, y, the conjugate is going to be, we call it z bar, and it's equal to x minus I, y. Okay, so I can put this down there. We can put a little dotted line down there. I'll make it a dotted, oops, I'll make it a little dotted line there to kind of highlight the difference, and I'm going to call that z bar. And that's the complex conjugate. And so every complex number comes in a pair with a complex conjugate, and they're always found on opposite sides of the imaginary of the real axis. Okay, so there's just mirror images across the real axis. So. And that's how we find it. So this operation of the complex conjugate merely just takes a negative of the imaginary part of the number, and that's that. So it's pretty straightforward. So, but it has some good. What about the algebra of this? Well, the algebra is pretty simple. So we have to see how this complex conjugate operation works with the algebra. So first of all, we know that you can easily verify that if I have two complex numbers and I add them together, that if I take the complex conjugate of the sum, it's the same as taking the sum of the conjugates. Also, if I have a product, ZW, and I take the conjugate of the product, that's the same as the product of the conjugates. Oops. Of two numbers. And the same thing for division. If I have the conjugate of the quotient, then it's the same thing as the quotient of the conjugates. And so on and so forth. So every basic operation we have, mathematical operation, works very nicely it commutes essentially with this operation of conjugacy. Okay, all right, so that's good. So this gives us also another way to write our complex modulus. Okay, so it turns out that, of course, if I have z, if I take its absolute value, now if I peel off the square root there, that leaves us with x squared plus y squared. Well, it turns out that's equal to z times z conjugate. And of course, we can see that x plus iy and x minus iy, and that's equal to x squared. And then, of course, the cross terms cancel, the imaginary cross terms cancel. And then what we see there is we have an I times an I, and that gives us a y squared. But because there's a negative sign there, that leaves us with a positive y squared. So now we have a nice way of writing our modulus in terms of products of a complex number with its conjugate. So that's a really nice, efficient way to write things. All right, so let's move on to the next idea. So we've done moduli and we've done conjugates. Another definition we need to pull out of the way is that of the triangle inequality. Okay, so the triangle inequality is it's a very much just a geometric. It's a geometric principle, or what you call a fact, in this case, of basic Euclidean geometry. And it's that, if I have two vectors, let's say, if I have z there, and let's say I have w there, okay? So those are two vectors. We can think of them as complex numbers in the complex plane. And now I want to take the sum of them, so z plus w. And what we do to add two numbers in the complex plane geometrically is you just take w and you attach its base to the tip of z, and about right there, let's say. And that represents z plus w. Okay, so we can write that as z plus w there. Now, we have this basic principle, or what you call this fact, is that, and I'll call it the as the crow flies. As the crow flies is always is always smaller than any other route. Okay, and that's the figure of speech way of saying this, and that just means that if I want to get to z plus w, if I want to get to this point in the plane from the origin, the distance z plus w is always going to be less than if I were to go individually to z and then go also on the route along the line w this way. Okay, and we can see that, and we see that forms that triangle here, the triangle like this. And that's why they call it the triangle inequality. And it simply means that if I take these two routes z and then also w, and I were to take them both together and add up that distance, it's going to be more than if I were to go directly to z plus w, the sum, as we've done there. Okay, and so and it turns out this triangle inequality will just be used a lot in any time we try to establish some other important facts about complex mathematics. It turns out this triangle inequality shows up a lot. So we just need to state it as a basic fact. We don't need to prove it here. It's a pretty intuitive thing to state. Okay, so the next thing we want to do is talk about polar coordinates. Of course, as with any vector or something in the plane, we have like this. I can represent it as an ordered pair of numbers, x comma y, in a Euclidean sense of going, there's x, and there's y. I shouldn't say Euclidean, but rather that that there's a we can use the xy coordinates to locate that point, or we could also use the magnitude of the vector, and we can call that r, and r will be equal to the modulus of z. Okay, that's equal to z. And also the angle, theta. Okay, so we know we can always write this as ordered pair. If we write it as a vector, we can always write it as r cosine theta times r sine theta. Okay, so that's pretty straightforward. But what we can use, though, we want to find an even more efficient representation in terms of r and theta, something even more compact than this ordered pair. And it turns out there is such a relationship, and that we have to use what we call Euler's formula. Okay, remember Euler's formula. I'll call it EF. Euler's formula states that e to the I theta is equal to cosine theta plus I sine theta. Of course, if I multiply this by r, if I multiply everything by r, we can see clearly that that is, of course, right here, that's x plus I, and that's my y. Okay, so now we have a really compact way. So now z, we can represent it as x plus iy in the standard xy coordinate system, or we could also write it in polar coordinates as r e to the I theta. Okay, great. All right, so now we have a really compact way of writing our function. And so another way, of course, we can write this is replace r with the modulus of z, e to the I theta. Okay, so of course that gives us the direction, and that gives us the magnitude. So we can represent it as r or the modulus of z, however you want to express it. There's lots of ways. All right, so let's just go with a quick example. Let's take z is equal to I, or e to the I, 7 pi over 2. Okay, so first of all, let's take note of 7 pi over 2. 7 pi over 2 is it looks like a radian. So this is always in radians, but this looks like actually pi over 2 plus 6 pi over 2, otherwise known as pi over 2 plus 3 pi. All right, so it looks like that the problem with polar coordinates and theta in general is that there tends to be a redundancy, is that theta, if you take it as a real value going from negative infinity to positive infinity, it leads to a lot of redundant representations. All right, so this 3 pi, of course, just spins around the circle 1.5 times, while the pi over 2 is really the important part that gives it some information. So let's see if we can better understand what's going on here. So if I do that now, so if I go, so where are we located on the circle? I said first we go to pi over 2. All right, and then we're going to do 3 pi's, so 1 pi, 2 pi, and then 3 pi's. So we end up down here. Of course, that is negative I. That's the location of negative I. So that means that z here is equal to negative I. All right. I could also write this in many other ways, though, right? I could write this as e to the I negative pi over 2. I could also write this as e to the positive I 3 pi over 2. All are equivalent in terms of their complex number that results, but we see that there's obviously a non-uniqueness in the angle. All right, so to do that, we need to just come up with some more formalism here and the notion of what we call the complex argument. So a new definition. So the complex argument. So first of all, I'm going to define it as arg with a lowercase a of z. In this case, we've defined it as arg of e to the I 7 pi over 2, and that's just going to return what the angle is. Okay, that's good, 7 pi over 2. But now if I talk about the principal value, so the principal value argument is a special version of arg that we're going to use a capital A for. And that's going to produce the negative pi over 2. So in general, the principal value, the principal argument of any complex number is going to be between pi and negative pi. All right, so this gave the unique principal argument of our complex number that we wrote. We started off as this definition. Okay, so now we have a nice way of writing our complex number. We can write it as the magnitude of the complex number, e to the I, the principal argument of the complex number. All right, so that is now our so we've covered a lot of the definitions here. So there's a lowercase argument, which is we can always write this now as the principal argument of z plus, in this case, it's going to be 4 pi. Okay, but in general, it's going to be some multiple of 2 pi. Anyway, so generally we'll take our convention to always be between these angles here. So what we're going to do is they call that we've taken our cut to be on the negative real axis. So finally, I wanted to go in and go find what is this principal argument. Okay, like I know how do we actually compute it? Given if we start with the representation of complex numbers as x plus I y. Right, so we have there the coordinates in xy plane. We have those rise and run. All right, so we want to find that out. So this is actually we're going to use the inverse tangent function, which has its own complexities, right? So recall then that that the inverse tangent. So tangent, of course, tangent of theta is a function that goes like this. And at pi over 2, it asymptotes to infinity. And also at negative pi over 2, it asymptotes at infinity. All right, and likewise, inverse tangent goes like this. It's simply flipped on its side, like that, and has a horizontal asymptote at pi over 2 and negative pi over 2. Okay. So that's the how we can write that out. I can write that as tangent w, where w is just this axis down there. Okay, so what we want to do is write this argument as follows. So what we really want to do is, the problem is, of course, we have to write it as this. Oops. This is going to be the tangent inverse of the rise over the run, and that's if if x is greater than 0. All right, because what we're going to do then is anytime if we have a complex number that's in the x is greater than 0 side, so the right half of the complex plane, that means that x is greater than 0, and that means we're between the angles of pi over 2 and negative pi over 2. All right, and so that works for y's that are positive, but also for other values here. So that value as well. So that gives that angle, or this angle here. All right, but what about on this side over here? What if x is less than 0 and y is positive? Well, we want to add something to it. We want to add something to it. So in general, though, we have to add something to this. So that has to be tangent inverse of y over x. Right, we have to add something to it. So of course, in this case, y is greater than 0 and x is less than 0, and that means this is a negative number. So it's actually going to be putting it down here. It'll give the equivalent value. Tangent inverse will give the equivalent value to the one that's on the opposite side of the circle. So what we have to do is add a plus pi to it. Okay, so that looks good. And now, likewise, if we have, so that's if x is less than 0 and y is greater than 0. All right, and what about tangent inverse? What about the case if x is less than 0 and y is less than 0? Well, in that case, you're over here, okay, and so that will be the number that gets spit out of tangent inverse y over x y over x in this case will be positive, so it'll be as if it were looking at that value, that complex number over there. The problem then, of course, is we need to then subtract pi from it. All right, so that gives us a way to write down the argument. That's how we can write it down. So that becomes the principal argument of our complex number. So it's a kind of a complex expression, but it works okay. All right, thanks very much.